Hello and welcome to Dissecting Computer Systems Lab. In this particular video, we are going to discuss about token economics. Now, in context of large language models, token economics refers to the unit economics, the operational cost, and strategic management of the tokens, right? That's a definition of token economics that a model will process. So, it means, in very layman terms, for any AI setup or an AI system, right, that is using an LLM that has an LLM integrated into it, right? And when we try to find out the total cost of operations, the TCO, that basically is measured in terms of a unit called token, right? How much tokens are you dealing with? Now, that's what we are going to explain in this video. Why is token a crucial factor in determining the cost of your AI system, right? As they mentioned that the API providers bills per token with both input token and the output token serves as the fundamental currency of generative AI. Now, that is the focus of this video to prove why token is a crucial parameter in finding the cost of your AI system. Okay, so before we proceed, let's quickly understand and have a basic idea about what token looks like. Right. So I'll just switch to the platform OpenAI.com, one of the tokenizer that they have, which GPT uses to tokenize its input. Now, say for example, I have a question behind explain token economics. How does token play a crucial role in determining the cost of our AI application? Um, this is what you will be feeding or a question that you feed into the GPT, right? That you have the chat GPT. Now, in the back end, this is how the tokenization of this prompt will be taking place. Now, you might see that each word is being considered as one token, right? And even the full stop is considered as a separate token. They are color coded. If you see, explain is one token, this token string is separate, economics as a separate, play a crucial role. Every word here has been taken into consideration as a separate token. Total characters in the string was 106, and the total number of corresponding tokens were 20. Now, what this means, not every character is mapped to one token. It's not that there's a one-to-one mapping between character and tokens. Otherwise, there should be 106 characters and 106 tokens. It's also not true that there is a one-to-one mapping between a word and a token. This might be misleading. This example actually might be misleading because here you see every word is being, getting one color code, which is one token, but that might not always be true. Say, for example, I copy this text here and paste it. Now let's paste just after this. Now see, what's the difference? If you see open AIs was one word, but here it has been split into three different tokens. Open AI apostrophe S is separate, right? Even for some of the words between, you'll find the same thing is happening. Even for the word tokenized, we have entered it as one word, but here it has been broken into token and ized as separate. Now, this depends upon the tokenization strategies. There are multiple tokenization strategies in place. We are not diving detail into how tokenization is done, but just to give you a very brief idea about what tokens are, I showed you this particular screen here, right? So it's clear that everything that we feed in as an input will be split into tokens. That might not be a character always, that might not always be a word-wise splitting. It might be a subword as well, like we see here in the word tokenized. The token was a subword of the word tokenized, and IZED was separate. So it might be words, subwords, or characters. And that is what token is all about. Now we'll dive back to our discussion on token economics to understand what and how are these tokens contributing to cost. So now we'll be dissecting a GPT style model step by step and mathematically prove why tokens are expensive. So here we have a GPT, the generative pre-trained transformer architecture. It has been taken from the ResearchGate, and this component actually from here till here is the GPT architecture. And if you dive deeper into the decoder component, this is the decoder unit. If you dissect the decoder unit further, the masked multi-head attention lies inside it, and this has been elaborated in this particular diagram. So it's not that the entire thing is a GPT architecture. This is the GPT architecture, and we dived deeper to it. To decoder, you get this architecture. You dive deeper to the masked multi-head attention, and you get this architecture. Now, since GPT stands for Generative Pre-trained Transformer, the word transformer itself is giving efficient evidence for the fact that the LLMs that we have, especially GPT, is built on top of transformers. And prerequisite before we dive further is you must have an understanding about how a transformer works, what is encoder decoder architectures, how attention mechanism takes place. Because this video will just focus on the cost aspect of it, not on the further details. Maybe in some new videos I'll explain them as well. So as I mentioned, transformers, right? So GPT is built using transformers. Now, when we talk about transformers, this is a transformer architecture, and transformers are encoder decoder models. Now, this is an encoder unit. If I highlight, this part is an encoder unit, and this second part is the decoder unit. So this is the decoder component, and this is the encoder component. Each of these have their own role. But to summarize, GPT uses only the decoder component. Hence, you see in its architecture, we just have the decoder layers. I mean, decoder component has been stacked on one top of each other, right? So, which means to conclude, we can say GPT is decoder only model. It uses a transformer, but it's not the encoder part, only the decoder part, right? If you're aware about how transformer works, you will understand why have we used only decoder in GPTs. So that's what we see here, the decoder 1, decoder 2, and so on to decoder n. This is the decoder stack, which means one decoder unit on top of each other, right? And this diagram that we have for decoder is pretty similar to this interior of the decoder component, which says we take in an input. Now this is important. What is X? Now you remember in the tokenizer in the uh, OpenAI's page, we had the color coded words, subwords, and characters, right? Each of them were a token, right? Each of them were a token. Now we vectorize them, right? We convert them into vectors of dimension d, right? And you get a matrix of dimension n cross d, right? That's what we have, input matrix of dimension n cross d. So each of the tokens that we saw will be converted to a vector of dimension d, and then we stack them on top of each other. So total n tokens of dimension d, it gives us n cross d dimension input vector. That will be basically, input to this GPT model, and hence you see here the x1, x2 till xn. Right? These are nothing but the input tokens is being fed as an input to the GPT architecture. Let's dive further. Some things to note. What we are going to prove is number of parameters is not equal to, or I mean not dependent on the number of tokens. Remember, number of tokens and number of parameters have no relationship. Parameters are fixed after training, and tokens affect the computation cost, not the parameter count. That's what we'll be proving. That tokens has nothing to do with parameter count. It has to do with the computation cost. I have my own note here. I'll just use it to explain you now how. So GPTs are decoder only transformer models, no doubt in this, right? Let's suppose n is the number of tokens. Remember the OpenAI website I showed you where we tokenized our string. So let's suppose we got n number of tokens there. D is the hidden dimension. You might use any word embedding, right? You might use any embedding that will be used to convert your word into an embedding. So let the dimension of that be D, right? So as I mentioned, if you have the different tokens, each of them will be converted to a vector of size D. right? D dimension vector, right? And if you just have n number of, for every token, if you have that vector, you get uh, input matrix X of size number of rows equal to number of tokens, which is n, and the number of columns is the size of the vector, which is d. So X will be basically n cross d, isn't it? That was the input we had. Sorry. Now L is the number of layers. Right now, what is the number of layers? That is the number of layers of the decoder. Right? You saw in the example right above, we had stacked decoder layers. Let L be the number of decoder layers you are using. This one. So let this is decoder and like n number of decoders. Let's not get confused with the different variables we are using because the diagrams have been taken from multiple sources. Each of them had their own label, but just for the sake of understanding, this n and this n is different. This is small n, this is capital N. We can, for our derivation, we will assume this is L. Okay, decoder 1, decoder 2, decoder 3 till decoder L, L number of decoder layers. Now, that's the input representation we have in place. N is the number of tokens, D is the dimensions of the vector, L is the number of layers. So each token is mapped to a vector of dimension D. Thus the input is X belongs to R n cross D. I mean, I hope you understand. Number of tokens, and for each token is of dimension D. You stack all the tokens together, right? T1, T2, all these tokens together. So what do you get? N cross D, right? Now, the decoder layer overview. This was the transformer, right? The transformer, and this was the encoder component, and this was the decoder component. I have extracted this decoder component here. So we're just going to dive deeper into the decoder component. Now, decoder layer overview, if you see, it has a masked self-attention and a feed-forward neural network. So this is the masked self-attention that we're using, the multi-head attentions, right? And a feed-forward neural network. Right now, for this video, we are focusing only on the feed-forward neural network and the attention layer. Reason is pretty simple, because majority of the cost, right? I mean, the maximum impact is given by these two component only, the feed-forward layer and the masked multi-head attention layer, right? If you see the add-on normalization layers, they have negligible impact. You will see it down in the video. Hence, we for our calculation, we are focusing on the cost by the attention layer and the feed-forward neural network layer. So for our analysis, we will be analyzing in terms of the parameter count and the computation cost, both. We will see what is the total number of parameters in the architecture and what is the total computational cost that's coming up. Now, if you're aware about how the calculation of self-attention is done, right? So what do we generally do in attention, right? Calculations. We compute the value of QKV, which is query, key, and value. If you see, this is our input matrix, right? X, and the dimension was n cross d, isn't it? This is the n number of tokens, and it has a dimension of d, the vectors, n cross d. Each of these, first of all, we project it into a query matrix, key, and value. So this is the trainable matrix, okay, trainable weights they have. We try to project it to a query matrix, key matrix, and value matrix. For converting it from the input matrix to the query or the key or the value matrix, we need to multiply it with this specific matrices. These are trainable matrices. Now, if you see, all of them have equal dimension. Right now, in example, you see 3 cross 3, right? But the dimension actually is d cross d. This is the dimension of these trainable matrices. So WQ, WK, WV. This is WQ, this is WK, and this is WV. W stands for weight. They are trainable weights. Okay. Now, the dimension of them are d cross d. Depends upon the embedding size. Now, let's compute. What are we doing? We are trying to convert this input matrix that we have of dimension n cross d, right, to the query matrix key matrix and value matrix, right? So for that we need to multiply x with wq and then x with wk, x with wv. Let's consider one multiplication, which is multiplying x with wq. Okay. Now, what is the dimension of x? The dimension of x is, we know, n cross d, right? And the dimension of wq is d cross d. So we are doing a matrix multiplication, and as per matrix multiplication principle, if you have a matrix of dimension m cross n and other matrix of dimension n cross p, right? So matrix multiplication is possible only these two values are to have to be same, which means number of columns in the first matrix should be equal to number of rows in the second matrix, and total cost of this matrix multiplication, okay, total cost, which means total number of multiplication operations which you will be doing here, will be this m multiplied by this component n dot p. Okay, this is the total cost of multiplying these two matrices m. So this m and n and p comes from here, the second matrix, m dot n dot p. Likewise, if I try to find the cost of performing one multiplication between this component and the wq component, it's equal to n cross d dot t cross d, right? We are doing this matrix multiplication. These are the dimensions of the matrix. So as per our formula, we have n into this term, right? D dot d. What does that stand for? Sorry, let me make it clear. This stands for theta n d square, right? This is for one multiplication between x and wq. Likewise, since the dimension of this and wk is also same, this and wv is also same, so the same cost will be incurred for all the three, right? So we have 3nd square. That's what we see. The cost of matrix multiplication is 3nd square for this part only. Okay. Now, that was for the cost of multiplying this to get this q, k, and v, which is theta 3 and d square. This is the constant we can skip, right? Now, what is the number of parameters involved, right? So you see each one of these has d cross d dimensions, and as I mentioned, they are weight matrices, and weight matrices are trainable. So total dimension is equal to d square plus d square plus d square, which is equal to 3d square, and we have an output matrix as well of the same dimensions, so d square itself. So d square plus 3d square equal to 4d square is the number of parameters involved in this process. Okay, so again, each of the cell you see is a weight, and this weight matrix is of dimension d cross d. And similarly for these, so we have d square into 3, which is equal to 3d square parameters. Okay, remember, this is only parameters. I'm not adding that to the cost. Cost is separate. That is matrix multiplication. We already calculated here, this one, right? This is just the parameters. Now, what is the next step? Next is the self-attention mechanism. Now that we had X, we used W, Q, W, K, W, V to convert them into Q, K, and V matrices. Now, this will be used to calculate the self-attention. Now, in basic words, I hope you understand what self-attention means. I mean, we try to capture the relationship between, or how the importance of one token with all other tokens, isn't it? That's what we try to capture in self-attention. So we are trying to calculate the attention. First thing that we do is QK transpose, because the formula of self-attention you see is here, right? We try to multiply Q with K transpose, then just normalize it with this division, and again multiply with the value matrix, and we get the attention scores, right? So first thing that we are doing is multiplying the Q matrix with the K transpose T. Now comes the interesting part. So here we had the dimension n cross d, right? And these matrices had the dimension d cross d. So these matrices had a resultant dimension of n cross d, isn't it? The resultant matrix will have the dimension this and this. I mean, if you're multiplying two matrices with these dimensions, the resultant dimension will be this. The n cross d is the dimension of query key and value matrix. Fine. We'll keep that as a note. So you see here, I'll change the ink. The Q has a dimension n cross t that we saw here, right? And the K transpose. K transpose is nothing but the transpose of this n cross t, right? So n cross d was a dimension of K. N cross d was dimension of K. If you transpose this, it will convert to d cross n. I mean, rows will become columns, column will become rows, right? That's what happens here. D cross n. These two components now, we are doing a multiplication. If you're doing a multiplication, it's evident that the cost here will be n dot this component d dot n, which is equal to order of d n square, isn't it? Right? So this will be the cost of multiplication here as well. We'll see that down here. We are calculating it now. What are we doing is element-wise interpretation. Each entry is shown by this element of the matrix, right? So that's what we're doing. It's a dot product between token I and token j. So you see, every token has to be, there has to be a computation between the to find the attention between one token with every other token. So the number of pairs we have is order of n square, cost per pair, order of d. They have directly derived here, okay? But I have already showed you the cost that we did here is order of n square d, right? For computing the attention. How did we get that? So once we had the query key transpose in place, we try to calculate the cost of performing the attention. So cost of this will be order of n square d. Right? I hope it's clear. You can just go back to the video and see again how we found out this value. Now what's next? Applying attention to value. If you see the formula here, so the formula says you have to calculate qk transpose. There is some normalization going on, then it passes to softmax, and then what we are doing is multiplying it with the value matrix v. Remember, the dimension of v is still here, and here, what was the dimension of the matrix? So it was n cross d, the input matrix. This was d cross d. This becomes n cross d, right? That was the dimension of all the three matrices. Fine. So here, applying attention to values. A is equal to qk transpose. We already did this, right? And if you see qk transpose, qk transpose, the resultant matrix was of dimension n cross n, right? So we have n cross n here. The v that we know is n cross d, the value matrix dimension. Now, what will be the matrix multiplication cost here? Which will it equal to n into d, which is equal to order n square d. All right, so now since we have already computed the cost of the self-attention component, now comes the feed-forward neural network. As per our architecture above, we know that the multi-head attention component is followed by the addition norm layers and the feed-forward neural network here, right? For simplicity, we are skipping the negligible contribution to cost by add and norm layers. The main dominating factors were the masked multi-head attentions and the feed-forward neural network layer. So we move to what is happening inside the feed-forward neural network layer and how is the cost getting calculated. So if we move to feed-forward neural network layer here, the expression is as follows. So first of all, every token is processed independently. Okay, we don't have all the uh, tokens being processed like dependent on each other. No, they are processed independently. For a token vector, remember one token vector, right, has a dimension 1 cross d, isn't it? One token vector has a dimension 1 cross d. Now that basically undergoes this flow. What happens first? We have two trainable matrices, W1 and W2 in place. Remember, this is a simple feed-forward neural network layer, right? Uh, First thing is the dimension of the W1 and W2 matrix. Both are trainable. First, W1 has a dimension D cross 4D because we want to project the input vector to a higher dimension and then bring it back to the normal, which it had initially, right? And so it has a dimension 4D cross D. These are just trainable matrices. What happens first? First of all, we do a dot, as per the expression, there's a dot product between the input vector and the W1 component. X was of size 1 cross D, and there's a dot product with W1, which is of size D cross 4D. And as per our matrix multiplication cost, we know the total cost will be 1 into D into 4D. It's 1 dot D dot 4D, which is equal to 4D square. That's what we have, right? Next is this thing has to be added with a bias, negligible cost again. So we are ignoring that. But it again moves to the activation function. So now activation function also has a negligible cost. Why? Because now whatever is the dot product of your X with W1, the resultant dimension is 1 cross 4D, isn't it? So you have a row and total 4D number of elements, right? Each of these, what will happen here is basically we are trying to find out an activation here, right? And the activation order is negligible, right? Because constant time, it just you just have to pass through a function, right? And you have to do it for all the 4D elements. So it's 4D dot 1, which is equal to order of 4D. Compared to this, definitely this is negligible because this is linear and this is a quadratic, 4D square compared to what you have 4D here. Hence it is negligible. We are ignoring this for our cost. What happens next? We have the second linear layer. If you see the second linear layer, right? So the calculation was once you have done with this, whatever is the result, we have a dot product with W2 whose dimension is 4D cross D. Now, so far our cost, I mean the dimension of the matrix you received from this is 1 cross 4D, isn't it? And W2 is again 4D cross D. The resultant cost again will be this into this value, right? So 1 dot 4D dot D, which is equal to order of 4D square, okay? And the resultant matrix again here will be having a dimension 1 cross D. It's simple, right? So 1 cross D will be the dimension of the resultant matrix. Now, what was the total computation per token? We see that this expression, I mean, multiplication of this part with this part took 4D square, and this part itself took us 4D square above, right? It took 4D square above. So for one token, remember we have taken only one X, one input token. So for one input token, it took us 8D square because 4D square for this and 4D square for this. Why? Because the expression told us sigma x W1 plus B1 W2 plus B2. This we did, it took us order of 4D square, and whatever was the result, we again did a dot product with W2. It took us again order of 4D square, so total order of 8D square. These additions have negligible contributions, same with passing them through the activation function was also, the cost associated was also negligible. Now, if for one token, this is the cost, you have n number of input tokens. Remember the colorful coding that the OpenAI's tokenizer had done um, for the different tokens, right? Whatever input you have sent. So we had a count n. So for n, the cost will be again n into your 8d square. This is constant, you skip it. So order of nd square is the cost associated with n tokens in the feed-forward neural network, right? Uh, we'll do a comparison down again. So what is the parameter now in the feed-forward neural network? We had two trainable matrices, W1, W2. W1 had a dimension D cross 4D, W2 had a dimension 4D cross D. If you see total number of trainable elements here is 40 square plus 40 square, which is equal to 8d squared. These are the feed-forward neural network parameters. Again, the parameters are independent of n, right? So you see n is independent, parameters is independent of n. There's no relationship between number of tokens and the number of parameters. What is the total computation per layer now? So let's combine all the components. We found out that the self-attention had a cost order n squared d. The feed-forward neural network now has a cost of order n d square, right? Total cost of computation in one layer, isn't it? So right now we're just focusing on one. Once you entered a decoder unit, D1, and then we're going to come out. What is the total computation cost incurred here? This is the cost. For the self-attention in one decoder unit, you can get a cost of order n squared d. For the feed-forward neural network, you get a cost of order n d square. Total cost per layer is equal to order n square d plus order plus n d square. Now there's a catch. Which of this is a dominating component? Because we have squares for n also, for d also, right? Now total computation across different layers. Remember the decoder stack D1, D2, D3, dot dot Dn. It's not that you have only one decoder layer in the GPT architecture, right? Or the LLM architecture. We have lots of n number of L, sorry, not L. Let's have it L, right? Remember, we label it as L. The total cost for one decoder unit is this. For L decoder unit, you just multiply the factor L here, right? So this is the total compute cost across the layers. If you talk about the parameter count summary, per layer, the cost is 12d square, right? Now, how did we come up with 12d square? Um, if you see the parameters, we had 8d square parameters here for the feed-forward neural networks. And for the attention, the number of parameters we had calculated was 4d square, isn't it? 4d square here. So you add total, it becomes 12d square. Total parameters again 12 into d square dot L for L number of decoder layers. So what exactly is the catch? You see the total parameters again is independent of n. There is no n here, right? Dominant term analysis. Now we are going to compare the two dominant term in the cost, n squared d or n d square. Now, definitely the number of tokens we are entering mostly will be a larger size compared to the vector size, D, dimensions of vectors. So we considered n as the dominating term and hence n squared d will dominate and the total time complexity here will reduce to order of n squared d. We consider that this will be comparatively less and negligible. Hence, we consider this term from the cost factor. The total computation cost, in the decoder is order n square d. Now that we have discussed the computation cost, inside the uh, decoder unit, which is order of n square d, right? Let's see how generation in decoder works. So what happens inside the decoder? Say, for example, I say AI is powerful, right? Now, the number of tokens, let's for simplicity assume this is the tokenization done. So we have three tokens in place. This entire token will be fed at once to the decoder unit, right? We have the decoder unit. It feeds into at once and will be processed. Inside the decoder, it will go through the attention mechanisms of feed-forward neural networks as per our explanations above. Now, total cost for these will be order of n square, right? That's what we see, which is equal to 9 because we have three tokens and let's say 3 square is equal to 9. What happens now? After these operations, you get one token with a maximum or highest probability. Let's suppose you get end as the predicted value. So what happens now? Your string, your query becomes AI is powerful and what are you doing? You already had three tokens. You generated and now the size of your input becomes 4, right? Because whatever you are generating one token at a time, and for the next prediction you need that into account, right? So initially I had AI is powerful 3. I use this to predict the fourth token, that is and once I have that in place, now I will use this to predict the fifth word, right? So now you have an input of 4, so this will be fed again to the decoder model, and the computation cost would be order of 4 square, which is 16, right? Now you get some word. Suppose now the prediction is powerful and intelligent. Suppose now you got a word called intelligent. So now now your words becomes AI is powerful and intelligent. And you predicted this word. Now intelligent will also be taken into context, right? Number of tokens now is 5. This will again be fed to the decoder to predict the next token. The cost of this would be 5 square, which is 25. If you observe carefully, what is happening is the number of computations is increasing. Sorry, the number of computation is increasing with the increase in the number of tokens taken into account. And every time you are generating a new token, you are increasing the count. See, initially you had 3, you generated one token, the count becomes 4. You generated one token, the count now becomes 5. And the costs are also exploding in order. Say I had 3 square plus 4 square plus 5 square, isn't it? Likewise, if you keep on predicting, it will keep on exploding. So it's like, going till n squares, right? If I have these terms also in place, it is of, if you see this series, the summation of this will lead to an order of n cube terms. Now, the question is, why is this, what is actually happening? Remember, the decoder models is you know built for predicting the next token, which means in order when I entered an input, AI is powerful. In order to get the fourth word, I had to understand the attention between all these words among themselves, right? So how is AI, the attention scores between AI with is with powerful. Similarly, the attention score of is with AI is with itself and powerful, and powerful with AI is and powerful itself. So every word with every other words we're calculating the attention, hence we got 9, right? Now when it becomes 4, you're calculating the attention scores in 4 cross 4 matrix, isn't it? You will have AI is powerful and AI is powerful and, right? And you'll compute attention scores. So number of computation is increasing. Hence, we see if you keep on increasing the number of tokens that is getting generated, it gets added to the context and this value increases. And if this increases, we see it leads to order of n cube. So what is the way out? So for optimization purpose, right now what we have is something called KV caching. So the idea is once you have calculated the attention of AI is powerful, right? You know the values of AI and powerful, how much the attention to be given, right? You don't have to recompute most of the attention scores here. So what is important is calculating the attention score between the newly token that has come in to this family with the other tokens. Only this is important. There's no point in recalculating again the importance of AI with is AI with powerful. That attention score we have already calculated above, right? That kind of optimization is done, and hence we reduce this order of n cube to order of n square. In some videos going ahead, I'll explain KV caching as well. That how did we reduce order of n cube very smartly to order of n square. It's just like avoiding the recomputation of attention scores, right? So that's it. So final, the cost that we have is order of n square. It increases. Every time you are generating a new token, you are adding a new token to the context. And we know if you have more number of tokens in the context, you are exploding the cost, right? Order of n square factor. So final insights, we have cost proportional to the number of layers, the n square d factor, right? Now tokens are expensive because each token interacts with all other tokens. This is where attention comes in, leading to a quadratic growth in computation. So what did we finally prove? That parameters define the model size, tokens define the computation, and computation grows as n square, right? So every token you generate adds not just one unit of work, but a growing number of interactions, right? Because every token generated, you have to calculate the attention with all other existing tokens, and that's why token decides cost in LLMs, right? Hence, the cost depends upon the number of tokens, which is n. So if you don't control tokens, you don't control cost. This is DCS Lab where we dissect computer systems layer by layer. I hope this video was quite interesting. We covered lots of mathematical aspects. Now you have an answer to the question why, with increasing tokens, the cost increases.